Prim's lecture. Today will be a lecture on minimum spanning trees of how to connect things together in some sort of network and minimize the cost. In a way, some ways it's easier problem than some of the problems we have looked at before. Things like network flow or shortest path, I think, are a little bit harder actually. So hopefully you'll be able to, so this should help you lead to some solutions to this problem. There are actually multiple ways of solving it, actually depending on what kind of network you have. And the first question we should probably ask is, why should we actually care, right? Why should this be an important problem? Well, if you have a network, well, you obviously, it's not network if it's not connected. But let's imagine you want to minimize some costs. So you have a weighted network. Let's think of them as an electricity network, or you need a connection, right? But you don't want to overpay for something. You don't want to spend too much time building these expensive wires, putting poles up and everything. So you want to minimize this cost of distance, for example, or cost. And so you want to connect everything. We all want electricity. And that's how the problem actually appeared originally in like 1920s Czechoslovakia, actually, I believe, about 100 years ago. But of course, it's been around longer, right? So you have multiple choices, basically how to connect, and you have to make the optimal choice. So it's, again, type of optimization problem, right? And hopefully you can see this from this picture, a sample network. So again, when I say network, that means graph, of course, right? So graphs could have multiple edges, of course, obviously, right, in vertices. But when you end up with a solution, minimum spanning tree, so we end up with what? We end up with a tree type of structure, right? By definition, right, spanning tree, right? It's kind of, well, again, obvious, right? So what does it mean? What's key property of trees is that they are, or they, no loops, yeah, acyclical or no loops, same thing, basically, right? So, now I guess we should see, so by this, also, so what's the maximum number of edges you will have? It's already on the screen, actually, but if you think about it, right? So you have, 10 vertices, 10 cities you need to connect. So how many connections do you need to make? Edges, how many edges do you need? You have 10 cities. If you have 2 cities, how many connections do you need? 1. So you have 3 cities. Yes. So what's the formula? N-1. Yeah, of course. Okay. So you're all awake this morning. Okay, good. So yeah, so obviously you need the n minus 1 or v minus 1 as it says here, right? So, but yeah, the book says, this is obviously the book you can use for learning, it says that there's some ambiguity, that there's no guarantee of unique solution, right? Because imagine if there's like a same cost edges, right? You will not know which one to use, basically, right? It will lead to multiple unique solutions, actually, right? If this was maybe, instead of 18, this was 2, right here, you could switch them around, right? And keep solution, right? Yeah, it will still work, right? So, again, so couple things we need to worry about when we're building a solution, when you think about solution is, again, we want to avoid, if you get a loop, that's not good, right? So if your solution, when you're building up, you're going to start building solution from some point, from nothing, right? Well, at some point, if you see a loop, that means you need to backtrack, or that solution is not good. You need to use something else, right? Of course, it turns out there's actually an algorithm for start with from the other way around, like we start from bottom up, right? Which is the most algorithms we will look at. There's actually a top-down algorithm, which we don't usually look at. Maybe if you have time, you can look up, where we assume we take all edges and we start deleting, right? So again, different tools we've been learned over this course, right, kind of come together, right? If you had this problem and nobody had ever solved this problem, right? So you can start from bottom up, right, which is usually, we start with nothing, start with just vertices. We keep adding edges in some way. We just need to figure out some way of doing it. So question now is, let's start with a relaxed version of this problem. Maybe I'll make it. Maybe I'll do some painting. But imagine if these were all one cost, right? Just one. Unit cost, right? How could we solve it? This problem, if it is all same cost, we don't care. We just need connection, right? What would be the algorithm then? If if it didn't have a cost. If it was just like, all same cost. Maybe I'll do some paint. I'm sure you want paint. All right. And I'll see if I can draw. I can see we got our pen tabs, or I can draw it, right? Yes. So I'll call it A, all right? And we'll call it, B. We'll have C. I just want the excuse to draw, all right? And we'll have like E, maybe some. I'll do E here, right? Okay. Now let's do some connections. And for now, I'll just right. And there's a bunch of this. Let's assume. Of course, we can do also maybe, right, something like this, right? So we assume the cost is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? 400, right? So, but come up with an algorithm. Oh, we solve this. You want the minimum spanning tree, right? So this means basically you want a list of edges which connect all of these vertices together, all these nodes together, but you don't want any loops. You want a tree. So I can think of multiple algorithms. Let's start with something simple. Like let's start with the A, right? What do you do?
You just connect each of the neighboring vertices with
Yeah.
your starting point, and then you from the next vertices you check
Yeah.
if their neighbors have any connections. If
Yeah.
they don't, then you connect.
Yeah. So what kind of search is this? Well, you can do a different approach actually, but let's say one of them.
Right.
You can do breadth first, I guess. Yeah, you can do DFS. You can do depth first also. You can keep going as deep. If you keep jumping, if you don't check all neighbors, right? That's going to be depth first. If you check all neighbors, that's going to be breadth first, of course, right? So either one will work, right? So just only thing you need to care about is whether you have already seen this vertex, right? Right. And whether you only have this connection, and if you only have, then you don't use. So this would be, let's see. I guess I'll use something like green. So you say, let's do BFS, right? So BFS would be like this. And let's say you do alphabetical sort. Okay, you check. Okay, B checks. Okay, you check OE. We don't care. We already been there, right?
You should also do from A to D.
All right. In this case, it's actually we get the complete solution immediately. So this is really boring, actually. So I should have another. I guess I should have as E. So which is not so obvious. Yeah. So let's make it a little bit harder, right? Yeah. A little bit, tiny bit harder. You're right.
Maybe name it not E, but some other.
Oh, so yeah, right. Let's call it. How can I correct it? Let's do this F. I meant F, of course, right? Yeah. That works, right?
Yeah.
So yeah, obviously, yeah. So you missed. If you're doing breadth first, of course, you immediately have all four, and then you check. Right? So you just say, okay, B. Has connection to D, no need to do anything. E, no need to do anything, right? And then you move to C, has connection to D, no need to do anything. E, of course, right? No need to do anything. And then you don't check. Well, you don't check. You check D next. Let's assume, sorted by some order, right? And you see, okay, B, no need to check. Do C, of course, you only have connection. And F, okay. Then you check E. Well, if you are counting number of additions, you can stop there, right? You check n minus 1 or v minus 1, you're done, right? You're guaranteed you're done, right? So yeah, so this is sort of like a, expanding search. So this approach actually could lead to also for us to have this complete solution to this when you have weights. Let's just start having weights, so we'll just need to have some way of prioritizing which edges to add, right? But maybe there's a cheaper cost, basically. That's the basic idea, right? So, okay. So let's try this. Let's try this approach. Let me put some cost here, maybe. Well, I'll do 10. Well, they have red, yeah. Oh no, I'm correct. I see. I meant right here. So on. Oh, come on. My brushes. What's up with this? I had a nice. Yeah. No, that's not. No, I guess I went. I guess I'll need to use a mouse for this. All of this. Control Z. Yeah.
You have to increase the size.
Yeah. Yeah. 10. Okay. Control again. Control Z.
There is in the left top corner.
Which one? This one here, right?
Yes.
Yep. Okay, that's good. So middle. Get there. Okay. All right, that's good enough. Okay, so we have 10. I guess I'll do like maybe 4.
91.
91. Yes. That's never gonna happen, right? 21. Like 5. Is that 5? Does it look like 5 to you? Yeah. All right. So what is this one? 7. I'm sure you all have practiced trying to fix your grades, right? Right?
Yeah.
Yeah. So, okay. Now we need some connection here, tau completely, right? Something like I don't know, 25, right? And do maybe here like 2, right? Obviously. Okay, so we have 1. Well, I guess we'll leave it at something like in 8. Yeah, that works. So 1 is a really good one for that. So I'll make like maybe 0 and 20, right? Okay, some really wild numbers here. Okay. So yeah, again, let's see approach. So the idea is that we don't take the expensive edges, basically. Given a choice, you just need one connection, right? So obviously the idea is that we don't need a connection. So the question now here, of course, is how the lemma, I guess the idea is that core idea is if there's a way of connecting it, some vertex to the rest of the network, right? Or to the graph, right? You choose which one? You choose the cheapest one, right? Obviously, right? Because again, you have to connect them all, so you might as well choose the cheapest one. So in this case, let's look at E, right? Let's look at E. Oh yeah, okay. If you look at E, right? Now, which one should we choose to connect E to the rest of the network? Which is going to be the connection?
Which is the cheapest from E to?
Yeah, to the rest of the graph.
Well, to C.
Yeah, obviously C, right? So this means this same rule. If you're given these 3 choices, obviously you're gonna take this, right? You're gonna take this route, right? You don't want to connect it with something expensive, right? Because there's no reason, right? Because safely, again, we just need a connection. It could be a long connection, right? Right? We just need a connection at all because so in this case this is gonna be C. So same thing again. So A, right? How is A going to be connected? What's the cheapest way to connect A to the rest of the network? Of course, B. We take B. And of course, that leaves us a problem, right? So you say, okay, we have A to B, right? You can see A. It's not yet clear how it's going to happen. So the question is, do we need this connection? That's a very good question, actually. Now, is this actually, well, it's cheap, right? And we need to connect A to, we need C in the network. I mean, of course, they have to be part of the network, right? So, the usual, there's a couple approaches, but one approach would be to sort all possible edges, right? That's one way of doing it, right? And start adding the cheapest ones first, actually, right? So we will do AB, right? AC, right? Well, actually, you do CE first, right? Because it's really cheap, right? And get the 3 wins immediately. So I'm gonna draw a solution, right? Just like roughly, you start with these cheap connections, and the only rule you need then is if this edge helps, right? Meaning, is it useful, right? Does it make a loop, right? If it makes a loop, we discard it because we don't need it. Means we already have. It's possible to have a really cheap route, but it's not already. We already had it previously something cheaper even, which was good. So we might need at some point. We need something expensive. For example, we need like if I do A, right? If you have this, right? A, F, G, E, this is of course starter, so again, this is of course, right, F, right, and so this is going to be G, right, G, right, G, right, so obviously, if this has like, this has, 9,000, right, we have no way around, we need that 9,000, right, so we'll have to use it at some point, yeah, but okay, so, couple approaches. So we could start just by sorting edges. That's one algorithm actually we'll look at today. We look at edges, say 2, okay, we need that. Look at the next one, AB, we need that. Let's look at 5, yeah, we need that. Now 7, yeah, we need that. And now 8, do we need it? No, we don't need it, right? So that's approach. How about 10? No, we don't need it. How about 20, right? I think after 10 is 20, right? We need it. And then 21 we discard, right? So 21 is not needed, 91 is not needed, 25 is not needed, right? 91 is not needed, and then we need 9000. So that's an approach. It's not the best algorithm, but it works actually, right? So it's one approach, it's just sort edges, right? The only challenge is the loop detection, right? That's the tricky part. You need some tricky data structures. The other approach is, maybe the simpler one is use the Dijkstra, kind of like Dijkstra approach, right? Start with some vertex, right? And get the cheapest one from that vertex, right? Right. So, because well, so what's the idea? Let's think about it. If you have some vertex, you obviously want the cheapest connection to the rest of the network, right? So it's a given, right? So we have a priority queue, just like that. So we have the 4, 5, 10, 21. We take A and 4, right? Like let's imagine this algorithm. So how this would work, or maybe like make something like this kind of color, right? So you do this, right? Oh no, come on, Control undo. Can take 2 colors. Yeah, that's it. So you do this one, right? Now what do we do in this approach? If you're doing it like sort of like Dijkstra type of approach, but it's simpler actually, right? You're not trying to find the shortest path. You're just trying to find connections, cheapest connections. So we have A, B connected, and we still have these edges from A, right? What do we need to do? We need to add to the priority queue what?
The next cheapest.
Yeah, Control Z. We need to add these 2 also to the priority queue, right? You'll still have this. We'll still do this next, but of course we'll need to add these 2 as candidates, right? Because we're expanding our network, right? So then of course we will do this, right? And again we expand. We add these as well, the CE, CD, and CF, and now our priority queue is changed, right? So we will do this one next, right? And then which one will be next? We add F, the 9000, and then 25, right? We need to add those, right? So basically, by this now, it seems like we almost have all the connections actually, right? We still don't have the E, right? There's not actually, we have all the edges possible in our priority queue, right? And then we take the cheapest one, which is of course going to be which one? We take which one?
A.
Yeah, A to well, this one is cheapest, right? We need this.
7.
Yeah, we take 7. We take 7, right? Okay, and then basically what we do is we check next cheapest one is what? Which one is 8, right? But it leads to the one we already now visited. We already have it. So we discard. We need this one, right? We discard. And we need this one, of course, eventually. So yeah, so let's see the name. If I keep always mixing up these names. When I teach this, I think this is Prim's algorithm, if I'm correct, or yeah, this is Prim's algorithm. This is so-called Prim's algorithm, right? And the book starts out with I think, relatively more complicated algorithm, which is better actually. It's a better algorithm. But Prim's, I think, is the simplest one, basically. Right, so let's see if we can implement this, right? Let's see if we can implement this Prim's algorithm. And I might have an implementation, right? So does this make sense? Because you guys know how to do a priority queue. I mean, obviously you would use an existing priority queue implementation. You don't have to do a priority queue from scratch, right? So, but the reason I teach is first because it uses something you already know. It's like a relatively simple data structure. The other ones actually need something a little bit fancier, need fancier data structure to use to work properly. Okay, so let's implement this Prims. Let's see if we have GitHub. Let's see, I have my GitHub open. Where is it? Come on, what's wrong? Why can't I? spanning tree. Again, here you see another example. Again, you can see this is a minimal spanning tree, right? Because obviously each wherever you have a choice, right? Right. For example, here 4 would be a stupid choice because of course 2 is cheaper, right? So same thing goes here, right? There's no need for 4 because 3 is cheaper, right? So again, so we have again, if you define these are obviously connected graphs, right? So obviously if you don't know what kind of graph you have, you will find out if there's no connection, right? You'll see it's a disconnected graph, right? You'll find it out. You're trying to find a minimum spanning tree, right? So it's a very well-known problem, right? Again, so as I mentioned, right? So we'll use prims first. I think I hopefully I do. Well, I don't do Kruskal's, but Kruskal. Let's see if I can move around actually these solutions. I think I did all of them already. Or do I have prims here? Yeah, I do have prims here actually. Right. So this actually I think is simpler, right? And then we'll go to Kruskal's afterwards, right?
I have a question.
Yes.
What exact problem does a minimum spanning tree is really needed? Because it seems very specific.
Well, like I said, anywhere you have connections, like a network, right? So you need connections. You need to keep this connectedness, right? Like I said, it's a classical example where it's used in electricity grids, basically, right? That's a classical example, right? So it turns out there are other problems where you find too, and I'm trying to think of good examples which are besides electricity networks, right? Well, of course, I guess you could say all networks, but that's where you want the maximum flow, right? But you just want the connection, basically, right? You are, like I said, you want to wire city, right? But you don't want to overpay, basically, right? It could apply to internet, of course, networks as well, right? So let's think again. I guess you could say social networks as well, I suppose, right? I don't know, but the only question, what would be a cost for social networks? Maybe, I don't know, cost of, what would be a cost for social network? Like, I don't know, cost of, spending, I don't know, sending email, I don't know, or cost of, it comes up quite a bit actually, right? But I can't think of good example. That's my answer right now. Besides the obvious ones, right? Like I said, the obvious ones. But if, like, for example, if like last week we talked about the maximum flow, right? Yeah. You can apply to also these bipartite matchings and other things, right? Too, actually, right? So it can come up more, maybe, right? So maybe this is less useful as far, but the approach here is actually more generalized. It's like the tools we already know, right, can be used to solve this, basically. I guess that's what I say it's important. Or of course, the answer could be, yeah, it's always taught. Yeah, this is like the classical problem. It's like hello world, right? but no. Because of these approaches, actually, it does come up sometimes, actually, right? So I'm telling you, of course, okay, let's say if you are like a real life problem, like you're building like some Android application, or like if you are at Google, it would come up, right? They have all kinds of network problems. If you are like two-person startup doing like an app, maybe probably not, right? So that's the actual answer, right? Like as many of these problems, right? But if you see but again, it's one of those things like, yeah, it doesn't come up for like 2 years, but then you see, okay, yeah, this is actually minimum spanning tree problem. Wow, I know this stuff, right? Yeah, this is right. Okay. Right. So let's look at Prim's algorithm before the break, I guess. Right. So again, reason I like Prim's first, because this is something we already know is a priority. We use a heap, right? Which already has we already have something initial, right? We pass in a graph. So we know, of course, the n. Let's look maybe a little bit bigger. Let's make it a little bit bigger. Oh, I put this one here, right? Okay. So again, the algorithm is any vertex will work, right? Because of course you have to connect them all, right? So when you have a condition, a while loop, right? While not all vertices are in a subgraph, find the current minimum weight for the vertex, minimum edge, right? With minimum weight, which is something outside your current what you have connected, basically, right? And then you stop, basically, right? When you find this one, right, you add the other connections from this new connection, basically, right? And that's it, basically, right? So this, I think, is, to me, this seems the easiest one to implement, actually, right? But it is not the most efficient, right? Why is it not most efficient? Because if you have also, if it's a dense graph with multiple edges, right, it will be a lot of extra work, actually, turns out, right? So E log V, right? And the problem is, of course, that if E is close to V, right, which is sparse, very few connections, right? This is a good algorithm, right, for sparse. But if it's very dense, this is not going to be good, right? So it's actually reverse, actually, right? So E dense, right? Actually E, right, is going to be pretty hard to use. So again, let's look at this implementation. Graph start where we start, right? We pass in visited. We use a set, obviously, because it's efficient, right? Yeah, for efficient membership testing, right? Obviously in O1, right? So we have the actual connections, right? So we start somewhere, right? So that's our connection. We add it to the visited, right? And then we make a priority queue, right, by weight, right? Again, in this case, we are using sort of our edges are in for start vertex, right? Let's look at this tuple, right? Edges are start vertex and E is the last, right? So weight, right, is first, right? Yeah. So that's our initial priority queue, right? We heapify it, obviously, so, right? But again, now, while we have, at least something to visit, right? Or we could check basically the length of this, of course, also, right? While we have, anything to visit, right? And we keep finding, right? We pop the current cheapest one, right? Right. And the thing is, if it's cheapest, right? If vertex is visited, right? This is O1 check, right? This is very cheap check. We can continue, right? Very cheap check, right? And otherwise, we add it. But now, right? So this is all good. The only last step to do is to add the extra new edges from what? From V. We have a new addition basically, and we add if it's not 0 weight, right, and it's not visited, right. So also notice this part here. We also checking again. Notice check again. E not in visited is a fast O1 operation. So we can do this, right? You have to be careful again. If visited was like maybe a list or array, it would be expensive, right? But it's a set. So we're just checking this, basically the set membership, which is very fast, and we add more of these operations. So this is pretty good, I think. Pretty clear algorithm, actually, right, to implement. Maybe we can do some improvements, I don't know, right? But let's see if this works, actually, right? So, and of course, how do we do the graph? Like, what's actual graph? How do we represent the graph? It's a length, right? And graph, how many items we have, right? But the question is, how do we, yes, there's a weight. I'm trying to see the representation of these vertices. So G, well, I'll need to do something, what's this, 0576500. This looks, I think it looks like a 2D list or no? Because I don't have it. Actually, let's figure this out. That's the hardest part usually, right? Trying to remember how did I represent the graph, right? Well, was it adjacency list? Was it matrix? Right? Probably two candidates, right? Right. Maybe something else, some esoteric, and of course, maybe you have this adjacency list. How do you represent edge weights? Which one is first, right? So in this case, Python is probably, in a way, it's easy to work, but if you don't have strong, like it would be nice if you had a class for edges and class for nodes. You could see what you're dealing with, basically. It'd be nice, good thing to refactor, actually, right? But, well, we have like, I don't know, a couple minutes, so I probably won't refactor it right now. But, so start vertex, okay, that's an, okay, and let's see, how do we find the, edge? Okay, we enumerate, okay, for an enumerate graph, right? So this looks like, okay, so that's of course the I is the index for that. And it looks like a matrix. It looks like a matrix representation. It certainly looks like it, right? Yeah, that's right. So I should probably add a note, right? Assuming it's correct note, right? So graph of Control Z. Find minimum, yeah, and parameters. Graph, yeah, AI is smart. Agency matrix, well, I don't know. Maybe it's not, but it looks correct to me, right? Output, right? Starting vertex, right? On a return list of edges in the minimum spanning tree. Looks good to me, right? And let's see, let's look at some simple example, right? Let's do really, this one is relatively complex, right? Spanning tree, MST. Let's do something simpler. Let's do new one, or maybe I'll make a new paint and do another paint. Can I do another paint? Will this work? Yeah. Okay. Let's do something really simple, like so, like 3 only. Let's do 4. Let's do 4. Okay. Again, and I guess we call it A, right? B, C, D. We'll make our connections. So again, and I'll do something like this, right? This is going to be expensive, right? So this will be like 10. This will be like 2. This will be like, I don't know, 6. And this will be 5, right? Okay. And this will be like, I don't know, 8. So obviously, what's solution? What's going to be the solution to this? We start at A. Well, it actually doesn't matter, actually, right? It doesn't matter. But we start at A. Which ones? We want to connect them.
Well, A to B.
Yeah. Then?
B to D.
Yes, correct. And then?
A to C.
Yes. Okay. And yeah. And now you were asking, okay, where do we start? If we start at C, right? Let's say we start at C. Is it going to be different? Let's take a look. We start at C. Which one do we check? We check C to A, right? Yeah. 6, right? Same thing, right? And we add, of course, we add A has what, 2 and 10, right? We check the next one is going to be in priority queue, is going to be A to B, right? And then, of course, B has also the cheapest one will be B to D, right? So yeah, so obviously the order of where we start is going to matter how we build up this tree, right? But the end result will be the same. Again, because it's undirected graph, we have connections basically, right? So it's not a two-way, it's a, undirected.
It's for all of the cases.
Yes. So yeah, it doesn't matter. Yeah. So you can start anywhere, right? Like I said, start with D, same thing, right? So we can taste it, of course, right? So let's see if we can implement this. Right. Let's look at this graph, right? Let's build a graph. Let's build the graph. So we have, well, okay. So I'll need to. Let's see. So of course it has to be symmetrical. So so here A is 0, B is 1, right? C is 2, and right is row 0, right? Right. Okay. Now so A to B is 2, right? 2, right? How about so A to C is 6, right? Right. And how about D 10, right? Okay. Now B to C nothing, right? B to D is 5, right? Yeah, 5. 5. And finally, let's That's 1, 2 for me. So 1, 2, 3, 4, right? And we need one fifth one, 8. No, yeah, 8. C D is 8. Yes. Okay. Right. So, and again, so we'll end up with, we can see already here, we're going to end up with these cheap ones, right? In this particular case, right? So, let's run it. Print. Yeah, for ONG. Yep. Okay. So I'll get rid of this and let's see if this works. I think it's going to work, but I don't know. No error. Oh, I didn't. Of course, I need to also initialize this graph, right? Okay, let's do it one more time. Yeah, so 0 to 1, 2. Yep, that's it, of course. 1 to 3. It's 5. This is 2 to 4, right? Yeah, D. And of course, 0 to 6. Yeah, well, that's the solution. All right, so let's take a break. Let's see, at 15 minutes, and hopefully we can find something. We'll look at some other algorithms afterwards, right? Maybe find a practical use case, MST.